So, oops, we're doing something called the test for increasing, decreasing. Oops, sorry, let me just turn my phone off here. We're going to be learning about when a function is increasing, decreasing. That is not how you spell decreasing. Oops, what just happened? Hello. Decreasing. And we're also going to be learning about maxima and minima. So really, we're going to be seeing how we can use the derivative and what the derivative will tell us about the shape of a function. So the first thing we're going to do is look at a graph. Let's say that I have a function that looks something like this. So my first question for you is, what is happening at these 2 points right there? In terms of derivatives, in terms of what we learned this semester, what can we say about the derivative at those 2 points that I just like put in pink?
Not differentiable.
Not differentiable. Good job. Why not?
Because it's on a corner.
Yes. So those 2 points right there they're actually cusps, but we'll say cusp, corner. So it is not differentiable there. Good job. Not differentiable. And that's going to be important to us in just a second. So now my second thing that we're going to look at about this is if I look at this portion of the graph right here, as x gets bigger, what's happening to y? As my x values get bigger on that little portion, what's going on with my y value?
Stays the same. Stays the same.
Say that one more time, David.
Stays the same?
On this portion right here?
Oh, okay. It's decreasing.
So exactly. So as my x value gets bigger, my y value gets smaller. So here we say that the function is decreasing. So what decreasing means, when a function is decreasing, that means as x gets bigger, y gets smaller. Okay. And so then over here, what happens to my y values as my x values get bigger? On this portion right here.
It's increasing, gets bigger. Y and x get bigger.
Exactly. So we say that this portion of the function is increasing. And that's because as x gets bigger, y also gets bigger. Okay, and then this right here, this like line that we have right there, that's straight, I think that's what David was talking about before. As x gets bigger, y doesn't change. Y is constant. So on that region right there, we say that the function is constant. And that is, as x gets bigger, there's no change in y. Okay, now if I go over here, so far so good. Any questions about what increasing, decreasing, and constant mean? Good. So if I go over here and I draw a tangent line on my curve, what's the slope of that tangent line? Is it positive or is it negative?
Negative.
So that's a line with a negative slope. So here we can say that the slope is negative. And what's another word for slope?
The A.
Derivative.
Derivative is another word for slope. So in other words, we can see that the derivative of the function where it's decreasing is negative. So in other words, derivative is negative. What about over here where it's increasing? What's the slope of that tangent line? Is it positive or negative?
Positive.
Positive. So the slope is positive, which means that the derivative is positive. And then what about here when it's constant?
Uh,
What's the slope of that little green line right there?
it's 0.
It's
like-
0. The slope of a horizontal line is 0. So the slope is equal to 0, which means the derivative is equal to 0. So these ideas right here of our slope being the derivative and being able to find that relationship between where it's increasing and decreasing and the sign of the derivative is called the increasing decreasing test, or the test for increasing and decreasing. So we're just going to kind of summarize in words the thing that we said right there. So the test for increasing and decreasing tells me 3 things. First, it tells me that if f prime is positive on some interval, so if the derivative is positive, we saw that that was the place where we had our function increasing. Then f of x is increasing. If f prime is negative, so if it's less than 0 on some interval, then f is decreasing. And if f prime is equal to 0, then it's constant. Okay, so this is our test for increasing and decreasing, and it follows pretty logically from looking at the function and from recognizing that derivative and slope are the same thing. So then the question becomes, how can I use this fact to find all of the places where a function is increasing or a function is decreasing? Now let me know when you guys have this down and you're ready to move on. All right, that's a whole bunch of you. Okay, so for increasing, we're gonna draw a little like arrow like that. And for decreasing, we'll draw a little arrow like that. And to understand how I can apply this test and how I can use this test to find all of the places where a function is increasing or decreasing, we need to understand what are the places where a function could change what it's doing. So, in other words, what are the places where a function can change? And so we're saying like increasing to decreasing, or decreasing to increasing, or increasing to constant, or constant to decreasing. So like, where are the places that a change can occur? If I go back and look at the graph that we have up here, where does the function change? Where does it change from decreasing to constant? Where does it change from constant to increasing? What can I say about the derivative at the places it changes?
Equals 0.
It's non-differentiable.
is not differentiable. It doesn't equal 0. We said that's actually happening at a cusp or a corner in this case. But David is right in that, so at this particular graph, we see that the change happens when the derivative doesn't exist. But what if I were to draw another graph that looked like, how did I draw this graph before? What color? Black. That looked like this. If I identify the places where this changes from increasing to decreasing, what can I say about the derivative right there? Good. So this is the case where the derivative is equal to 0. What about this? If I have it increasing, and let's say that I have a jump discontinuity. What can I say about the derivative at a jump discontinuity?
Doesn't exist.
Doesn't exist. So here we have that changes when derivative equals 0. And here we have that it changes when derivative does not exist. And that's the same thing up here. I'm going to go back down in just a second. The same thing up here. It changed when the derivative does not exist. So these values where these changes could happen, where the derivative equals to 0 or the derivative does not exist, are what's called critical numbers or critical values. They're called critical because they're super important. They're the place where things happen in functions. So here we'll have a definition. If a function is defined then x equals c is a critical number, which you will often see as a critical value, and I think I'll probably use the word value more than number. Sometimes you'll even hear it said as a critical point of f of x if f prime of x is equal to 0 or f prime of x does not exist. So these are the things that make a number a critical number. The derivative is 0 or the derivative does not exist. And these critical values are the only places that a function could change what it's doing, from increasing to decreasing, decreasing to increasing, decreasing to constant. They're the only places it could change. And this is super useful because it gives me some guidelines for how I can apply that test for increasing and decreasing. So the first thing I want to do if I want to apply that test is to find my derivative. My goal being to find the critical value. So I'm going to find the derivative of f of x. And since our goal is to find critical values, we're finding the places where f prime equals to 0. That's the same thing as finding horizontal tangent lines. And hopefully you guys remember that to find horizontal tangent lines, we always want to simplify the derivative. So up here, we're going to say find f prime of x, and we want to simplify it because our next step is going to be to find the critical values. And these critical values, as we just said, that's when f prime is equal to 0 or f prime does not exist. And I remind you that f prime equals 0, those are our horizontal tangent lines. Which is one of the reasons we've spent so much time this semester calculating horizontal tangent lines. You'll remember it even showed up on your midterm. So then my next step is I'm going to create what's called a variation table or a table of values by first making intervals using the critical values. So we're going to set up a table of values, which you will often see called a variation table. And then we're going to find the sign of the derivative at one point on each interval. Okay, then we're going to apply the test. And so we'll see this in a problem in just a second. Use the test. To determine what f is doing on each interval. So these are my guidelines for applying that test that we saw up there. So again, once again, let me know in the chat when you have these guidelines down and you are ready to do an example problem where we follow them. All right, that's a bunch of you. Okay, so we're going to look at an example. We want to find the intervals of increase and decrease of f of x is equal to x to the 4th plus 1 over x squared. And our first step that we have up there to follow our guidelines is to find f prime and simplify. So what rule do I need to calculate f prime here?
Quotient rule.
You got it. I'm gonna have my quotient rule. I have like f and g. So I will have f prime of x is equal to the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. Now we want to simplify, and remember when we're simplifying to find horizontal tangent lines, we want the greatest common factor of the numerator. What is the greatest common factor of the numerator here?
X.
It's not just x, x is going to be part of it.
2x.
2x, there's also a 2. If you don't bring the 2 with you, it's honestly not that big of a deal though. So we're going to factor out a 2x, and that's because inside of this 4 right here, we can think of 4 as 2 times 2. So there's a 4 inside there. What's left over in my first term when I factor out the 2x?
2x squared.
No. I have a 2 left, and then I have an x cubed and an x squared. So how many x's do I have there? 5. How many did I take away? 1. So I took away 1, which means I have 4 left over. So this is actually 2x to the 4th minus x to the 4th minus 1. And that's because we're subtracting x to the 4th plus 1 in parentheses, so the minus sign gets distributed to both things. So then I have 2x times x to the 4th minus 1 over x to the 4th. Is there any? So, Xavier, because we're asking ourselves, it's 2x is the GCF, because we're asking ourselves what occurs on the left side of the minus and the right side of the minus. So I start with that 4, and I'm like, is there a 4 on the other side? No, but there's a 2. And I know that 4 is equal to 2 times 2. So that means I can take the 2 out. Then I move on. I'm like, oh, I have some x's. Is there an x on the other side? Yes. There are 5 x's on the left side and 1 on the right side. So I take the 1. Does that make sense? Well, we're going to do it again in the next problem. So I can talk about it more in a second if you need me to. Right now, though, can I simplify this anymore? You sure? Do I have like a factor of x on top there? I have this factor of x on top and this factor of x on the bottom.
The 2 after.
What was that, Ellie?
I don't get why you took out the 2 after, like 2x4.
Okay, I'll explain that again in just a second. We'll redo it again in just a second. Let's finish this first, and then I'll go back and I'll re-explain that first step, because I think a couple of you are still having trouble. So here, I have 1x on top and 4 on the bottom, so I can actually cancel 1 out. So I have 2 times x to the 4th minus 1 over x to the 4th. Now I'm just gonna look at the numerator here, because it seems like some of you are still struggling with the greatest common factor and with understanding what happened here. Okay, so this is my numerator, right? Now what I'm doing is I'm trying to find my greatest common factor. So I'm looking at the left side and I'm trying to find what is on the left side that's also on the right side. Looking at it like this might be a little confusing for you guys, but we can use our rule here to say that this is x to the 5 here minus x to the 4th plus 1 times 2x. So that's x to the 5 because I know that x to the a times x to the b is equal to x to the a plus b. So now, when I start with the 4 here, I'm thinking of 4 as if it equals to 2 times 2, right? So I could actually even rewrite this as 2 times x to the 5th minus x to the 4th plus 1 times 2x. So I'm like, oh, hey, look, there's a 2 on both sides. That's going to be part of my greatest common factor. And then I'm like, okay, well, the next 2, there isn't another 2, but here's x to the 5th. Okay, so on the other side, there's also an x. Which one has the lower power? That power of 1 is lower. So that means our greatest common factor is 2x. Did that help?
Couldn't we just multiply 2x by, oh no, it's a product rule, never mind. Yeah. Confused.
So like when we're simplifying, we know that our first step is always to try to pull out the GCF. And so like that's what we're looking for. Like, what's the GCF? What can I pull out?
But what if we just did 2x times x4? Then we would have 2x5.
We would, and it would be much more challenging from there to figure out how to set it equal to 0.
Okay.
So like, if you'll think about it, in the past, one of the things we've done is we've said when we're simplifying to find horizontal tangent lines, factoring out the greatest common factor is definitely going to be the most efficient way to do it so that we just immediately have everything in the form necessary. But then when we were doing higher order derivatives, we were like, simplifying works differently for higher order derivatives. So it's kind of like in our head, we have simplifying for horizontal tangent lines, we should always be looking for a greatest common factor. And because these critical values, we know that we're going to set f prime equals 0, we want to simplify in the same way.
Yeah, but then why did you just like take off the 2x for it later on?
I didn't. I factored it out. So like now when I factor out I factor out the 2x, right? So I'm like, this is 2x. What's left over in the first term?
2x4 minus 4, x4 minus 1.
2x4, and then I have minus x to the 4th minus 1. But then I'm like, what is 2x to the 4th minus x to the 4th equal? Like, what does this subtraction give me here?
X to the 4?
X to the 4, exactly. So that's what happened there. I like
Okay.
combined my like terms.
And then how did you take out the x? Wait.
So then this right here, I thought of that as if it's like x over x to the 4th, right? Because it's all factors, I was able to cancel out one of those x's.
So, but what, then, give me a second, because I can't see. So then why is it still x to the 4 at the end? Over x
Oh,
to the
because
4?
that should be an x cubed, my bad, thank you.
Okay.
Thank you. That should be an x cubed there. Okay. Some of you had asked me the same question privately. Is anyone still confused as to how we found that greatest common factor and factored things out to simplify this? Okay. So that brings us to our second step. And our second step is to find the critical values. And our critical values come from two different places. They come from when f prime is equal to 0 and from when f prime does not exist. And so f prime equals 0, that's finding our horizontal tangent lines. So we've said when we have something like this, it's the same as setting the numerator equal to 0. F prime does not exist, that's going to be division by 0. So this is like division by 0, which means that I'm setting the denominator equal to 0.
It could also be a root of a negative number, right?
It could also be a root of a negative number, but for this type of problem, I don't think you have to worry about that.
Okay.
But yes. Okay, so f prime equals 0. I'm taking my numerator and I'm setting it equal to 0. So that gives me x to the 4th is equal to 1. So I want you guys to be careful here. When we have an even root, we always have to do plus minus. So this gives me plus minus 1. And then when f prime does not exist, we're setting that denominator equal to 0, and we just get 0. So here I have 3 critical values. And those three critical values are x equals -1, 0, and 1. And now, at this place where f prime does not exist, we know that there are three options for what that could be. It could be a discontinuity, it could be a vertical tangent line, or it could be a corner or a cusp. I want you to get into the habit of checking if it's a discontinuity. That's going to be important for us later. So what I want to do here is, if I plug this into the original function, do I get division by 0? I do. So I want you guys to get in the habit of doing that. Plug into original function. What I end up with is 0 to the 4th plus 1 over 0 squared, which is 1 over 0. What does a constant over 0 mean I have?
Infinite discontinuity.
Yeah.
You got it, Kiana. An infinite discontinuity, also known as a vertical asymptote. So this is a vertical asymptote or an infinite discontinuity. And for this particular problem that we're doing right now, that's not important. But we're going to come back to this problem later, and it is going to be important. So I'd like for you to try to get in the habit of just like checking that every single time. So that brings us to our next step. And here we're going to set up our table of values. So I'm going to start by making my intervals. So it said make intervals using the critical values. So I'm going to start at -infinity. What's my smallest critical value?
-1.
-1. And then I'm going to close, and then I'm going to go on to the next. I start where I stopped. What's my next critical value?
0.
0. And then my next one?
1.
1. And then I don't have any more, so I'm going to go all the way up to infinity. So here, this is my step 3. I just created intervals using the critical values. So the next thing I'm going to do, if we look at our step 3, it says find the sign of the derivative at some test value on each interval. So my next row here, I'm going to have as my test value row. And I'm going to pick a random number on each interval. So here I'm going to pick -2, here I'll pick -0.5, here I'll pick +0.5, and here I'm going to pick 2. So here I'm picking a number on each interval. And then the next thing I'm going to do is plug those numbers into f prime to find the sign of f prime at those numbers. So f prime is 2 times x to the 4th minus 1 over x cubed. And I need to know what is the sign at each of those values. So I'm doing f prime of -2. -2 to the 4th minus 1 over -2 cubed. And we've seen this type of thing before. I really only need signs here. So I see that on the top it's positive, on the bottom it's negative, which means that here my answer is that it's negative on that interval. And here I have positive, negative over negative, and I get that it is positive on that interval. So you can plug these things into your calculator, but you can also just kind of do the sign of each factor like I'm doing right here. And that might be a little bit faster sometimes. So then f prime of 1/2. 2 times 1/2 to the 4th minus 1 over 1/2 cubed gives me positive, negative, positive. So it's negative, and then this last one is going to be positive again.
If we don't have any values where it's equal to, I mean, it's discontinuous,
Mm-hmm.
so we have never does not exist. Wouldn't it be safe to say that from calculating the first one, every next one is going to be the opposite? Because it has to be, no?
So not necessarily. The reason for that is, and if you think about x cubed, it actually happens in x cubed. So like x cubed looks like this. It does this, and then it does
Okay,
that.
right. Yeah,
And
yeah,
right
okay.
here, the tangent line is horizontal. And so it actually keeps increasing after that horizontal tangent line.
Right.
Okay, so I'm actually going to write this thing down here. We determined at the beginning that that was a vertical asymptote. At 0, there was a vertical asymptote, so I'm just going to write that down there. Like I said, we're going to come back to this problem, and it's going to be important in a little bit. Now, negative. If the derivative is negative, did we say that the function is increasing or decreasing?
Decreasing,
Decreasing. And if it is positive?
increasing.
You got it. So this is my final step. My step 4 is right here. It's to make conclusions using the sign that I got. So then I can conclude that f of x is increasing on -1, 0, union 1, infinity, and it is decreasing on -infinity, -1, union 0, 1. And that's my final answer to this question.
If they were to ask for local minimum or local maximum,
That's what we're about to do right now.
oh, okay.
Yeah. Okay, so are there any questions about this problem? Okay, so what David said, just asked, is actually what we're going into next. So actually, I'm gonna just write another line here. Check sign of f prime at each point, or at each test value rather. And then we apply the increasing decreasing test. Okay, so next. There are actually other conclusions that I can make from this variation table without doing any extra work. And those conclusions are about what's called extrema or maxima minima. So we're going to make some definitions and look at some graphs, and then we're going to go back to that problem and answer another question about it. So we'll just start off with some definitions. A function f of x is said to have an absolute or global maximum at x equals c if the y value is bigger than any other y value on the whole function. So in other words, it's higher than anywhere else. And if it's lower than anywhere else, it's called an absolute or global minimum.
Wouldn't it be if, like for the second one, wouldn't it be if the y is smaller?
Yes, thank you. Did I write bigger? I definitely did. Amazing. I'm just thinking the same thing. Thank you, Pam. Smaller. So let's just look at a graph of these things. Okay. The graph on the left here, if I look at this point right here, I think we should do that again. Is that point bigger than any other y value?
Yeah.
Does the function ever get bigger than that? So this is my global max. And you'll hear me use the words absolute and global interchangeably. Either one works. So sometimes you'll see global, sometimes you'll see absolute. So this is my global max. I'm still on the left. Does this function have a global min? No. So there is no global min because the function goes down forever on both sides. So it's going to keep always getting smaller and smaller and smaller. So this one has no global min. What about over here? Does this one on the right have a global min?
Yes.
Yeah. So this is my global min, the place that's lower than everywhere else. Does it have a global max? No. No global max. What about this? So this looks really similar to the previous one. Does this have a global min? No.
No.
What about the global max here, though?
Yeah, it's the.
So the idea being that
like,
these two things have the same y value. So in this case, actually, we say that they are both global max. So when the y value is the same at 2 points and that y value is higher than anywhere else, same y value. In that case, we say that they are both global max. So in other words, a function can have more than one global min or max as long as it's higher or lower than everywhere else, right? So if it's the same y value. So a function can have more than one global min max. Okay, so let's keep looking at the functions on the left side. Neither of them has a global min, but is there like a minimum value here? Is there a place that's kind of like a minimum? Those are what's called relative or local mins. And this right here is a maximum, even though it's not higher than everywhere else, it's still a maximum. We call it a local max. So this is a local max. This is a local min. And you'll also see that called relative. So a relative or local min is when it's lower than everywhere else around it. And it has a relative or a local min if it's smaller than everywhere on the small interval around it.
Can there be two local minimums or two local maximums if they're equal?
There can be an infinite number of local mins or maxes. And I'm going to show you that in a graph in just a second. Okay. When you guys have a moment, tell me in the chat, does this function have a global max? Yes or no? Does it have a global min? Yes or no? So just say max, yes, no, min, yes, no. So I need to know what that no goes with. Xavier. So you should be saying, max, yes, no, min, yes, no. Good job so far, guys. All right, good job, guys. So that's quite a few of you have answered. So the answer is that it has a global max. That global max is right here. So that's my global max. And this has no global min. But if I look at it, that is higher than everywhere around it. That is higher than everywhere around it. That is higher than everywhere around it. Is my global max also higher than everywhere around it? So that global max could also be considered a local max because it's still higher than everywhere around it. So these are all local max. And this is also a local max because higher than everywhere around it. How many local mins does this have?
4.
You got it. So there's 1, 2, 3, but then we have another one right here. So these are all local min. So I have one global max that is also a local max. I have 3 other local max. And I have 4 local min. And what is the derivative at every single one of these?
0.
0.
0. There is a horizontal tangent line at every single one of these. Now that's not the only thing that could happen to have a global max or a global min. I could also have, for example, something like that. How many, does this have a global max or a global min?
No.
So this has no global max, no global min. Does it have a local max and a local min?
Yeah.
Yes. What's the derivative at those places?
0?
No, not 0.
Sorry,
Points that
doesn't
are
exist.
They don't exist.
Doesn't exist. So in other words, local max and min occur when the derivative equals to 0 or when the derivative does not exist. Which, guess what, we just gave a name for? That's critical values. So it turns out that this is a theorem called Fermat's theorem that basically tells me that local max and min occur only at critical values. And what Fermat's theorem specifically says is that if f has a local max or min at x equals c, then x equals c is at critical value. So another way of saying this that maybe makes more sense is that max and min only occur at critical values, but not all critical values are max and min. For example, do you think that a max or a min could occur at a vertical asymptote? No. Max and min do not occur at vertical asymptotes. And we'll just remind ourselves critical values are when f prime equals to 0 and f prime does not exist. So this right here gives us a test that's called the first derivative test. That basically just repeats the same thing but in test form. suppose that C is a critical value of a continuous function f of x. And the first thing and if we look at this graph, we can kind of make sense of this. If the function goes from decreasing to increasing, I have a min. And if it goes from increasing to decreasing, I have a max. So this is what the first derivative test tells me. It says that if f prime changes from positive to negative, so in other words, I go from increasing to decreasing, then I have a local max. If f prime changes from negative to positive at C, so I'm going down and then I'm going up, but then I got a local min. And if f prime does not change signs, then there is no max or min at C. So when you have this down, let me know, and let me know if you have any questions about what this test is saying. Okay, so while you guys are getting this down, we're gonna add a thing. This f of c exists is a super important part of this test, which is why in the last question that we did, we checked about that vertical asymptote. Always check if f of c exists before applying this test. So you should be letting me know in the chat when you're ready to move on. Okay, that is at least half of you at this point, I think. Okay, so find local extrema. Local extrema, this means the local max and min. Now you'll notice, hopefully, this is the same function we were dealing with earlier. So I'm going to, right here, say, see variation table from previous example. So let's go back up to our previous example and look at that variation table. Here's my variation table. Look how I drew those lines. I can kind of imagine that the function is decreasing and then increasing. So what do you think is happening at -1?
Local minimum.
I have a local min. I change from decreasing to increasing. If I look at my arrows, I can even see that this must be a min. At 0, I'm not even going to think about it because I've already checked that it was a vertical asymptote. And what's happening at 1?
Local minimum again.
Local min again, it's going down and then it's going up. So that's also a local min. So notice that to apply the first derivative test, I'm just using the variation table that I already have. So I'm going to go back down here and say f of x has 2 local min at x equals to, what was it, -1? And x is equal to +1. When we are asked to find local extrema, though, we always want to find the y values. So we're going to find our y values by plugging into the original function. So here I'm going to be looking at f of -1. And that gives me 2. And then I'm looking at f of 1, which also gives me 2. So my local min are at -1, 2, and 1, 2. And that is the answer to this question. There are no local max. Is that enough, Alejandro, or do you need more? Okay, so in the last 5 minutes, we're just going to do one problem from like start to finish. We're going to find the local extrema and the intervals of increase and decrease. It should go pretty fast. I think we can do it in 5 minutes. I'm waiting. I'll give you guys a few seconds first. It's no local max. So if we look at like a graphs, like look at the graph to the right here. That had a global min, which was also a local min, but it was just no local max. If I look at my variation table where I was doing this, there is one place where I changed from increasing to decreasing. And that's what our first derivative test said. If we change from increasing to decreasing, then we have a local max, but there cannot be a local max there because there's a vertical asymptote, right? So the only place where the local max could happen is a vertical asymptote. And so it's therefore not a local max. Does that make sense?
If it was discontinuous, let's say, if there was,
I think I can answer your question without you finishing it.
Okay, yeah, go ahead.
So the answer is that if it's discontinuous, then we definitely don't have a local max or a min. I'm going to go back down and show you what, like, let's say that we have a removable discontinuity. Hang on, I'm going to keep that up so that people can write. Let's say I have a removable discontinuity. If you think about how we defined our maxes, it said the y value is higher. Is there a y value there?
No, there's none. So.
There's no y value. So when it's discontinuous, the only time that the y value might be defined would be if I have a vertical asymptote and we have something like that. That's not going to be a max. Or if I have like a jump, right? And that's also not going to be a max or a min.
Okay.
Yeah.
All right.
Was that your question?
Yeah, exactly.
Okay, okay, let's do one last question real quick before I let you guys go. I'm gonna kind of rush through this one, but I'll only rush through the parts that aren't important. Hopefully. So we want to find the intervals of increase and decrease and the local extrema of f of x is equal to 4x plus 1 over x. And my step 1 is to find my derivative. So I'm going to rewrite this as 4x plus x to the negative 1, so that f prime of x is equal to 4 minus x to the negative 2, or 4 minus 1 over x squared. My step 2 is to find my critical values. So I want to know, where does f prime equal to 0? And this type of equation we've actually solved numerous times. Actually, maybe not numerous, but we've solved at least twice. So first I'm going to add 1 over x squared to both sides. Then I'm going to multiply both sides by x squared. Then I'll divide by 4. And so what x values do I get here?
Plus or minus a quarter?
You got plus or minus a half.
Half, sorry.
Yeah, plus or minus a half. You got it. Okay. Are there any questions about how I just solved that equation there? So then when f prime does not exist, remember that's division by 0. So that's when x squared equals 0, which just happens at x equals 0. So I have 3 critical values here. X equals negative 1/2, 0, and 1/2. Do I have a vertical asymptote at x equals 0?
Yeah.
I do. I got that constant over 0. That means I have a vertical asymptote. And guys, I know that I'm rushing through this a little bit. I just won't want to keep you too late. And I want to reassure you that I am going to keep doing this type of problem next class. So don't stress about it too much. That said, it is on your web work. Okay, so that is a vertical asymptote. So then in my step 3, I'm now going to set up my variation table. And I'm going to write I for interval. I'm not going to write the actual interval every time. So I'm going to have negative infinity, negative 1/2, negative 1/2 to 0, 0 to 1/2, and 1/2 to infinity. And then I'm going to write TV for test value, f prime for the sign of f prime, and then f for my conclusion. So I pick a test value on each. So I'm going to pick -1 and +1. And here I'll pick -1/4 and +1/4. What function am I plugging those values into?
The original function. Oh, f prime of x, the derivative that we just got.
Yes. Good. So I'm plugging them into f prime. So this is the part I'm going to really super rush through. I'm just going to give you guys the signs here. So this is plus, minus, minus, plus. So here we plug these values into f prime to get the signs. Now, remember, we already checked at 0, there's a vertical asymptote. And then, based on the sign, I can make my conclusion. What do I have at -1/2? Is that going to be a max or a min? If it's going, you got it. It's going to be a max. It's going up and then down. And what about at 1/2?
Minimum.
A min. Okay, so that means this is increasing on -infinity, -1/2, 1/2 to infinity, and it is decreasing on -1/2, 0, union 0, 1/2. And then I have a local max and a local min. Local max at -1/2, 4. And this is because f of 1/2 is equal to 4 times 1/2 plus 1 over 1/2, which is 4. And a local min at +1/2, 4. Wait, hang on. -1/2 is -4, my bad. Okay, so here are the parts I rushed through. We're just like, I gave you the signs and I gave you the y values. I'll try to let you guys go a little early next class to make up for it. But that's all for today. Unless you guys have questions about this, largely though, like the first problem we really went through, so I think you'll hopefully be able to figure it out. Next class we'll do ones that have more challenging equations to solve for the critical values. But that's all.